Hello and welcome to the next episode of EVM programming course. And now we will quickly go through some of the EVM quirks that might be strange. I also want to shed some light on them, why they are done like that. So those are the list of quirks I prepared for you today. First one is silent underflow and overflow. This is what you already saw in the previous episodes. And what does that mean? If we have a number 0 and we subtract anything from it, it will roll over to the biggest number and then subtract from it. So this is super strange, but this is actually the simplest way that you can implement that. I don't know if you know, but this is actually how processor works. So in your processor, if you have 64 bits architecture, which most of the people have, you have also the possibility that you are having number A and number B. You are taking the number together and you add them and they overflow. Normal thing, it may happen. However, the difference between EVM and processor is that processor sets a special flag. This is called the carry flag. And carry flag means that, listen up, there was an overflow or underflow. And we know that overflow may happen only when add is executed, and underflow may only happen if subtraction is executed. So it was done because of simplicity of it, and the EVM machine had to work as low-level assembly that processor is used. So that's why it's done like that. Next one, there are no floating numbers, which I do believe is really, really, really good. And why is that? In many financial systems, people are not using floating numbers as well. They are doing the same thing that is being done in Solidity. So for example, you have a number and its precision. So in case, as in Solidity, you have a number that has 18 decimals precision, and this is called WAD. And you have Ray. Ray is 27 decimals precision, so it's 18 plus 9 additional decimals precision. It's super useful when you have, for example, some accruing interest. Normally the interest accrues by block, by second in Solidity, so you need really, really small precision to be able to not have issues with, for example, missing rewards accrual because some function is being called really often. And as I said, the financial system for the most crucial calculations also usually is using that. And the question is, why? Why can't we use normal floating number for that? The answer is that it's super hard to have the precision when we are using different notations. Let me give you an example. What is 1 divided by 3? Of course, you know from the math lessons that is 0.33333 to the infinity. So how do you express the infinity in finite number? You can't, so we are usually rounding it. And if you think about it, if you had ternary system, when like in binary we have 0 and 1, in ternary system we have 0, 1 and 2, it would be super easy to express this number in ternary. However, in our decimal notation number, we cannot. We can either round it or use the infinity notation, which of course computers don't use. A personal story here, I'm doing Java development for nearly a decade right now. I had many strange things because of that, especially if you want to compare two numbers and they are floating numbers and they should be equal, however they are not. So for example, if you have a number 1.0 and then you do that, you would expect that the result will be 1.0, right? However, many times I had this string number. Of course, it is not 1.0, but 1.0000, all the zeros and 1 at the end. It stems from how do you even express the floating number notation. So this is easy. So we have this ERI 754 format that is describing how the floating numbers may look like. It's outside of the scope of this video. However, you may check that if you want. However, the way that it's expressed makes it that 1.0 times 1.0 is not equal to 1.0 because of how the little issues it may have. And we already have serious problems with rounding without that in Solidity. So just imagine how worse the problem would be if we added floating number to the mix. I think that the amount of hacks that we had would like at least double. Next one is constructor returning code to be deployed. You normally don't see that. However, for example, if we have our contract from previous episode, if you define a constructor for yourself, even if it's empty, as in this case, it does nothing. However, Solidity injects the code for you. And the code that it injects, it just takes all of these functions code, the function selector that allows you to tell which function you want to call, and all this stuff, packs it together. And at the end of constructor, implicitly, this is what you are not seeing, it added all these bytecodes and says, okay, I put all of this that I want to be deployed to on-chain, I put it into memory from this offset and of this length, and it returns it. So it returns a byte array that is then used to be deployed to the chain. So now you may think, okay, so what if I use low-level assembly and return it? What will happen? This is actually really fun because you would have a smart contract that is being deployed, and in this case it has 0 length. So this also means that you can create a smart contract which has no code and has a default code hash. However, it has storage variables assigned, and it's considered as deployed because even though the code hash is empty, it is still being there, and the nonce of the contract is 1 at the moment, because contracts, when they are deployed, they are starting with nonce of 1. So this is strange behavior, but this stems from how the EVM treats deployment of contracts. Okay, return data size to load 0 to stack. We saw it in the previous episode when we were dissecting the minimal proxy contract. I already mentioned it, so if you haven't seen that, please go to the previous episode. I already mentioned that as well. Deploy 0 code address with storage. If you return 0, the contract will be deployed. If you set any storage variable before, then you could just read it off-chain what the storage variables are there, without the contract having any logic inside. Concerning expensive storage, I already covered that in the episode about the gas. So generally I/O operations, that means any operations that the processor has to go and read something from disk, it takes super long time. We don't see it normally if we are running our computer, but I saw somewhere an example that reading anything from the storage is like having all the ingredients in your fridge, which is your processor, and then if you have to call anything from I/O, it's like, you know, traveling to like a different town that is 100 kilometers away for this one single ingredient. So this is the difference between reading something from memory and reading something from the storage. That's why it has to be really expensive, because otherwise you could create smart contracts that can lead to denial of service of node. And then we have stack limitation, memory, and call stack limitation. So call stack limitation is really limited by the gas limit. So there is no explicit amount of call data that is limited. So no one tells you, okay, you can just pass 1,000 bytes of call data up. Above that, it won't work. But you have to remember that you have to pay for each call data byte. So if your call data takes more than available block gas space, it will just revert on you. Concerning memory limitation, we have this quadratic memory expansion cost. And this is because if you, for example, just allocated like gazillions of bytes, the underlying node executing the code would have to allocate like thousands, 10,000s of gigabytes. And of course, no node has that. So it has to be limited to, again, prevent from denial of service attacks. In case of stack, it's just normally stack machines do not require as much elements as memory, and this is why there is distinction between stack and memory in Solidity. If you have something small, you are putting it to stack, which is 1024 elements. If you have anything bigger to put, you are using memory. Next one, this is not a quirk, but this is something that is very specific to Solidity. You have deterministic execution. That means you do not have any random function. If you want to achieve randomness on chain, you can have that. You cannot, at least not the randomness that would be required to run your programs, because we right now have a prev randal that is included in every block header. So this is a random number picked by validators. However, validators can modify it to an extent, especially the last validator that signs off the block. And apart from that, we have what is changing, like previous block header, and like reading information from previous headers is also kind of non-deterministic, because like it can change, but it's deterministic if you think about it at current time that you are executing transaction. If you are executing it now, at this moment, there is nothing that is different between nodes. So each node, if we have, for example, block number 1000, we have this timestamp, which is common at this block number for everyone. We have prev randal, that is common to everyone. We have previous block information that are common to everyone. And there is no change. And this is actually required to fulfill the biggest requirement, which is that it has to be deterministic for every node to take some previous blocks, re-execute it in the same manner, and make sure that they have the same result. That's why actually Solidity is permissionless, because we know that whoever in the future joins the network and they verify the chain from the genesis, from the first block, and they apply the transaction that took place, they will end up with the same state of the blockchain that the nodes that are currently being run. As a trivia here, for example, there is problem with Cosmos. Many implementations using a Cosmos ecosystem are having problems with this determinism. And the problem is that in underlying language, Golang, the maps, just as Solidity, we have mappings. So the mappings in Go are non-deterministic. If you want to iterate over them, like you are almost guaranteed to have different results on each run. So you should not use maps for deterministic iteration over them. And there are many problems and many vulnerabilities in some hacks due to this very fact. So this is actually really cool that Solidity has that. And the last thing, I remember when I first learned about Solidity and how hermetic it is, me coming from the big corporations world and coding of systems that have interactions with many external systems. I was like integrating dozens, if not hundreds of different systems in my life. So it was super strange for me. It was like, okay, this is cool, but this is actually useless. So if you have this closed box and you have no interactions with others, how is it useful? How can you use it if you cannot like use any outside systems? And then of course I learned about oracles, about Chainlink, and how you can do your own oracle, and it then made sense. And it actually also makes sense if you think about it in the context of the previous item, the deterministic execution. What if you had connection to an external system and read some external data, if it could, for example, information at this given timestamp year ago, if it read this information, and right now you read the same information from the external system, and now the answer is different, now all the nodes that are re-executing the state, they are ending up with having a different worldview than you. And this is problematic because it leads to chain splits. Okay, that's all for today. I hope you learned something new, and see you in the next one.